currently in my PY year. Yeah, I'm currently in my PY year. I work at Amazon Robotics, and most of my work at Amazon deals with object tracking. So it's a very interesting concept, and I'm really excited to talk about it. Uh, 1 second. Okay, so what is object tracking? There can be like two trains of thought while you think of object tracking. We can track the movement of pixels, like feature pixels across multiple frames, and we can track actual objects, so bounding boxes around objects across multiple frames. And we want this tracking to be extremely like robust. So depending on the orientation of the object in which it was seen on the first frame, like we also want to track the object if it was been rotated in different scales and angles, and also if the object has been occluded by certain other like obstructions during the frame of motion. Um, so there are many fields in object tracking. There are some classical methods such as optical flow and feature tracking, and you get to other methods which use some more math with the Kalman filter, which brings in some motion information while tracking. And then you can also get into deep learning methods in which we use identification features of each bounding box. And then with that, we can map features from previous pictures. So optical flow, it's like one of the first classical methods that I'll be discussing here. It's just the apparent movement of objects across a visual scene. So for each pixel on our frame, we want to know what's its XY velocity. And essentially, that's what we're calculating, a vector field for each pixel. And this depends on the orientation of the observer. So it's relative to the observer and the visual scene. The main equation for optical flow starts with that. So considering a pixel x comma y at time t, after a delta t, it moves to that location, x plus delta x, y plus delta y, and t plus delta t. Now the t plus delta t is just another coordinate. It doesn't mention the actual location. It's just to show that the pixel has moved to that location. And we know it'll be the same pixel. So the intensity I of that pixel will also be the same after it has moved certain distance. Now, using the pair series to approximate that function, we get first term, then second order terms, and then the higher order terms. And by removing the higher order terms, since they're very small, and we know that this intensity of xyt is the same as the intensity of the moved pixel, we get that equation. So it is the relative change in the intensity with respect to x, y, and with respect to time. And that's equal to 0. So dividing by t, we get that equation, which can be written as that. So in optical flow, we want to calculate those two values, Vx and Vy, which is the velocity of the pixel in the x and y direction. Now, before we go forward, this is an equation in two variables, and we can't solve it right now because we don't have enough equations to start with. So almost every approach to solve this problem introduces more constraints to solve it. And one of the most popular methods is the Lucas-Canard method. So this method was initially given for image matching. So matching features between two different images, but we can also be used for optical flow since that's essentially what it is, matching the same pixel across multiple frames. So the author assumes that all the pixels are in a given neighborhood have the same apparent motion. So we can apply the same formula from the previous slide, the bottom one, and say that all those pixels have the same xy velocities, and then giving them in a matrix equation. So AV equals to B, and we want to solve for V, right? So in this case, we have n equations solving for two values. And we can solve this using least squares. So least squares, essentially, we want to find a value for v such that AV minus B is minimized. Essentially, the error of AV minus B, that's the error, is minimized, and that's solved using this equation, where we do A transpose, AV equals to A transpose B, and then we get that. Before I go to the next slide, there is one, I guess, glaring issue with this. Can anyone spot it? Sure. Exactly. That's the first thing that people in Lenal should notice. How do you invert this? You can't just put it like that. So yeah, the matrix A should be invertible, and the transformation should not be too small, which means the eigenvalues lambda1 and lambda2 should not be too small, and they should also be relatively equal. So for those who don't know, eigenvalues are values. Essentially, almost every transformation will scale certain vectors by certain values. Those vectors which just get scaled are called eigenvectors, and this gets scaled by these eigenvalues. So for our 2 by 2 matrix, we have two eigenvalues, lambda1 and lambda2, and these values can be solved using matrix reduction. So what does this imply? These pixels where we get these conditions are just corners. So when you think of a corner, you have points with extremely rapid intensity changes in multiple directions. And the matrix ATA is just a sum of the intensities of the pixel in the x direction, the y direction, and then the xy and the xy multiplied. So it's the top left corresponds to the intensity change in the x direction and in the y direction as well. And that's how we get those two values, lambda1 and lambda2, to be extremely large, because we want that gradient to be extremely big for both the values, and which signifies that it's an edge. And this is an extremely good place to calculate optical flow, because that's how the condition gets satisfied. Now, the issues with this is that it's, again, computationally expensive, because this function gets applied to each pixel and that needs to be run for each frame. That and the aperture problem. If we have, let's say that's our camera, the square with the circle in it, and we take a frame. The actual object can be that checkered pattern, and it could be moving in any of these directions, either top left, going up, or sideways. But the video that we get would just be these lines going along the diagonal, and we cannot figure out in which way are these lines moving. Are they moving up or angled, or are they moving sideways? Because these are technically just edges. So we cannot solve for motion in this case, which is why we need to have corners. And with the corners, we can get the condition from the previous slide and solve for that. Another disadvantage is that this algorithm doesn't account for occlusion. So once a pixel goes behind some obstruction, you can't track it anymore because it's gone. There's no more information about that pixel. So yeah. And now we get to SIFT, scale invariant feature transform tracking. So in this case, we want to track features across different scales and different orientations. So there are 5 steps in this algorithm. This is 5 steps. I don't want to go over them. I'll go over them in detail right now. Before I go over them in detail, this is what's called a convolution in 2D. In other words, applying a filter. So whenever I say we apply a filter with a function h, It's essentially taking a matrix, which is H in this case, and applying it to each pixel, row by row, column by column, adding up all the values, and that'll be the output of our new image. So we can apply filters to do all sorts of operations on images, such as blurring, figuring out gradients, much more. But that's the general formula. And it's just to give, and this diagram, this animation is just to give like an intuitive understanding of what's going on when I mention applying a filter. The Gaussian filter. So the Gaussian function is that, and the filter in 2D is given by that equation as well, x squared plus y squared divided by the sigma. And when we take a filter with images, we need to take discrete values. So we just sample the Gaussian at n by n points, and that gives us the picture on the right. And the color responds to the intensity of the filter at all those points. So imagine this filter across an image. So for each point, we're essentially taking the average of all the points around it and summing them up, and that'll be our new value. So we're essentially blurring each pixel, and the new image that we get will be an overall blurred image. This is another filter called the Laplacian of the Gaussian. It's defined by that formula. It's just the second derivative with respect to x, summed up with second derivative with respect to y of the Gaussian, and then we normalize it by multiplying it with the sigma of the Gaussian. And the shape of this filter looks like that. And if we take the actual matrix, it gives us this. And this is used to essentially detect edges in pictures. So points of rapid intensity changes in every direction, because this is like a circular filter. We can apply it across the entire image, and then we get the edges. Now, one issue with this is that whenever we perform calculations with this, it gets a bit computationally expensive to calculate these derivatives for large Gaussians. So we use another filter called the difference of Gaussian filter. So let's take two Gaussian filters with two different sigma values and subtract them. When we subtract them, we get a shape that's extremely similar to the n-log filter. And it's way easier to calculate. And again, it gives us a good approximation. So this is just the 1D representation. The 2D. I'm not too sure, actually. Yeah. I'd assume it's just less calculations. Sorry? Oh, yeah. Yeah. Okay. Yeah, so like the actual way it's applied is a bit different. I'll talk about a bit more. But yeah, like you mentioned, it's easy to compute, and it gives a good approximation of the n-log filter. Okay, the first step in SIFT is we want to track features across different scales. So if I have a ball in one picture and the same ball, but that's zoomed in a different picture, how do I get the scale information from that? So what we do is we apply the Gaussian filter from the previous slide, and we apply it with different sigma values. So in each of these, so you see like the green pictures, we apply it with different sigma values, and that gives us different levels of blurring. So the first picture might be very slightly blurred, and then at each level, we apply more and more blurring. So this, when we do this, we're trying to eliminate certain information so we can detect blobs at different sizes. I don't have a good picture to explain this, but that's how the blurring effect works. And then, since these are all Gaussian blurred images, when we subtract the pixel values of any two pictures, we get the difference of Gaussian filter applied to the actual picture from the beginning. And this works because the convolution operation, we can just apply it on multiple pictures and subtract them together instead of doing the actual difference of Gaussian operation first and then applying the convolution. Associative? Is it associative or commutative? One of them. Uh, but yeah. And that's how we get the difference of Gaussians applied here. And these pictures on the right, they essentially show the edges of different blobs at different scales. Since we calculate them for different values of sigma. Now, for each of these different scales, we calculate the extrema. And the extrema is calculated in a 3 by 3 by 3 neighborhood for each pixel, for each scale. And what this gives us is that we want to find in which, for which value of sigma do we get particular interesting features. And for when you see the edge filter, the edges have really high values, really high intensities. But these edges depend on the value of sigma that we used here. If you use a different value of sigma, we can get edges that might not have been detected with this sigma, because an edge at a different scale might just be a curved line, but in a zoomed out view, it'll be a sharp edge. So that's why we use different sigma values and we get different edges. And we calculate the edges. We calculate the features by finding the extrema across scale and across space. Now, like I mentioned, by doing this, we get corners because corners also have really high intensities at the gradients. But we'll also find out that we'll get edges from these feature points. We knew from optical flow that finding feature points on edges is bad because of the aperture problem. Like, we won't know in which way that they're technically moving, and we just want corners. So using a very similar equation where dxx dyy is the double derivative of the intensity at x comma y, it just shows how much the intensity changes across x, across y, and across xy. And we calculate the eigenvalues once more. Here, a and b are the eigenvalues. And we know from the previous slide that we want a and b to be high and to be relatively equal. And that's the condition for corners. And in the paper, they use this equation r plus 1 squared divided by r with that value, and only for values of r less than 10, this is kept. Okay, so now we get all those feature points across multiple scales. We filter them out from the previous slide, and now we have all these feature points. So if you look at this picture here, it's just all those feature points mapped out, and the circle shows the scale at which scale was that feature point detected. So with which sigma value. Now we also want to do orientation assignment. So if I have a car in one frame that's at one orientation, but the car is rotated in a different frame, how do I match the same car to the next frame? I know the scale will match from the previous slides because we scale different sigmas. How do I get the direction? So what they do is they take a neighborhood around each feature point, and for each pixel in that neighborhood, they calculate the gradient of the intensity. So in which direction for each pixel is the intensity going in the highest direction? and they plot that direction into a histogram, and whichever direction has the highest number of pixels, that will represent the principal orientation of that feature point. So it's just to give another information, like a direction information for each feature point. And yeah, that's how it's calculated. Now, for each feature point, we have three values. We have the XY location, we have the scale, and we have the orientation. But we want a stronger, I guess, descriptor or like a signature that uniquely defines each feature with not just this, with not just these three values. So what the paper does is that they take a 16 by 16 window across each pixel, and for they break it into these 4 by 4 blocks. And for each of these 4 by 4 blocks, they perform a similar histogram function where they calculate the directions, but only in a direction. So like north, west, south, east, northwest, north, yeah. And then for each of the 4 by 4 blocks, they get the principal orientation of those 4 by 4 blocks. And this makes a new vector with 128 values. And that gives us a feature vector. And this feature vector is the descriptor for that fifth feature. Now, using this descriptor, we can match features across multiple frames. And they're just done using Euclidean distance with nearest neighbors algorithm, where like we just plot all the points, and then for each point, we find the nearest matching neighbor. So what SIFT has done so far is that we can track points, feature points across frames, and that'll give us the movement of pixels across frames. But I want to track objects, like a bunch of features across multiple frames. So we get to a new paper. In this, we select our feature points with a rectangle, and we initialize two objects. Two models, the object model and the background model. So the object model contains all of our feature points that we want to track, in this case, the person's face. And the background model initializes all the feature points that are in the background that we don't really care about, but they are important later on. So whenever we get a new frame, we want to match the feature points from the new frame to the feature points in our object model. And we also want to update the object model and the background model for any new feature points and any new background feature points. So the actual algorithm goes like this. So for each new frame, you calculate the SIFT descriptors, the 128 vector, a 128 valued vector. And then we find that the distance between the new vector and pre-existing descriptors within the object set and the background set. So we're trying to see, once we get a new value, how closely does it match with pre-existing values in our object set and the background set. So D0 is the distance between the object set, the shortest distance from the object set to our new value, and DB is the shortest distance from the background set to our new value. So if it satisfies that condition, it means that this new value is our feature object because of the ratio. And if it's not, it most likely belongs to the background. So we assign it a value of -1. This is just a simple cost function for a new value. And then we sum up all the cost values for all features inside our bounding box. And now we also want to calculate the bounding box moving across frames. So we define this function tau, and it's proportional to O1 minus O2, where O1 is the center of the box, height H1 and H2 are the heights, W1, W2 are the widths, and the last function S deals with aspect ratios. And then this was multiplied with a constant to scale it. So this function, it penalizes moving the bounding box very far and moving it and scaling it a lot. So it wants the bounding box to move slowly and stay relative to its previous position. And then we calculate a match score with the bounding box function and the cost function for all the new points. And we want to maximize this. So we find, yeah. Oh, it's just a constant, a scalar. Yeah. And we want to maximize this match score. So we find the bounding box. Sorry? Yes, but like that's not the problem at hand. Like we just want to track across frames. Like so even if the camera moves, um, I don't care about that because I just want motion information, not a relative motion information. So yes. Yeah. Yeah. So we want to maximize the cost function and you find the best bounding box that does that. And then we update the model with the new feature points that we just detected. So with this, we can track the bounding box moving across multiple frames. And the best part about is with this is that now we can handle occlusions because of the cost function for the bounding box, it penalizes bounding boxes that move a lot. So when we have occlusions, like the pigeon in this case, so the pigeon blocks the people from the camera, but because of the cost function, the bounding box does not move that much. And once people re-arrive in the scene, we can calculate the SIF features once more and the tracking can resume. So that's a good thing. It also works extremely well with scale. And also, like once the object starts to rotate, we learn new features of the object. And the model also updates these new features. So yeah. No, the bounding box is around the object that we want to track on the picture. What do you mean around the object model? Yeah, so just think of it like as a set of points. Yeah, it's just like a set of points that we want to track. Yeah, and then like at each frame, we match the new set of points that we get with those two sets and see how closely they match, and that's it. Yeah, it's not like a deep learning model yet. So, and this works surprisingly well, and it's super good. Yeah. Now, why can't I go front? Yeah. So now we get to some deep learning approaches. So a really popular approach with deep learning is sort. And how this works is that they use an object detection model to first get the bounding boxes for each frame. Then they estimate the future position of these bounding boxes in the next frame. And then based on these predictions, they try to associate the bounding boxes of the next frame with the predictions to get a final result. And then they also try to manage the lifespan of these tracks across the entire video. So the detection used in the paper is an FRCNN, and that's a two-stage detector. So the way detection models work, there's like two popular methods, like two-stage and one-stage detectors. In two-stage detectors, they have network. The first network will give out predictions of regions in which there are potential objects that we can find. And the second network, and like in the same thing, they'll have one more network to refine these predictions. And those are uh, relatively slower than one-stage detectors. In one-stage detectors, it's just one network, just one feed forward pass, and we get just the output of the bounding boxes for the input picture. So, like I mentioned in the paper, they used FRCNN, and that's a two-stage detector. I want to talk about YOLO just because it's YOLO, and this is the architecture. Don't want to go too much into detail, but that's that. The reason why YOLO works so well is because of certain four like techniques that they used. So initially, they break each image into an n by n grid. In this example, it's 4 by 4. And for each grid, they come up with this vector. So the probability that an object is contained in the grid, the xy width and height location of that object in that grid, and the presence of classes like car, person, ball, so on and so forth. So, and then the problem essentially just becomes a bounding box regression problem. So we have our picture. Our picture breaks down into 4 by 4 grids. Each grid contains this vector. So now we have 4 by 4 times 8 in this case. No, 7. Yeah, so we have a 4 by 4 by 7 vector, and that'll become a training set for each picture. And then we'll have multiple pictures, and then we perform regression. And that's how the model gets trained. The cost function is done by using intersection over union. It's just how much do bounding boxes from predictions intersect over the actual total area from the ground truth. And then once we get a bunch of detections, it uses non-max suppression to filter out the detections. And for non-max, it's just, it takes the, for a particular object, it takes the bounding box with the highest probability score, and then it tries to eliminate bounding boxes that have very high IOU with that first bounding box, does this over a loop, and then it will end up with just one detection for each thing. And that's YOLO. So now we have the bounding box from YOLO. How do we predict the next state of the object moving? With that, we use a Kalman filter. So this is a bit math heavy. So the Kalman filter is used to predict the dynamical models in real world applications. So in our case, we just assume that all the objects have constant velocity. And we just take like a measurements of objects at each state. And with that, we try to update our Kalman model. So the Kalman model is an iterative algorithm, and it learns more and more at each state and gives us slightly better predictions at each state. So we want to predict movement, right? And we have a bounding box. So we want to predict XY direction movement. Also, how much does the bounding box change in size and aspect ratio over time? So we have XY, which is the position, A is the aspect ratio, and H is the height. And then those four values are their respective velocities. So in our case, it's a 4-dimensional case because we want to predict 4 values, but I'll explain the process in just 1 dimension. So imagine a car going on a straight road, and we have a sensor that can figure out the car's position at time t, like a GPS sensor. So the car has a position and velocity, and the value, I mean, the distance of the car at a time t can be modeled with that equation xi plus v times delta t. And in our case, we just ignore the initial xi for simplicity. So the matrix F is called the state transition matrix. It just defines this equation in a matrix format. So given the previous position of our car, multiplying it with this matrix gives us the new prediction. And this prediction is that vector, the position along with the velocity. Okay, so this works all well. The issue is the Kalman filter doesn't give a prediction by itself. It tries to predict a particular variable as a point from a distribution, a PDF. So when we have a PDF, we also need to worry about how uncertain we are of our prediction. So we introduce this matrix P, which is called the covariance matrix, and it's just the covariance between our two values that we want to predict, the velocity and the distance. So based on how high we set these values, that's how uncertain we are of our predictions. And these values, they get updated across the process of the algorithm once we get new values that we sense from our GPS. And the value, P gets updated using that equation. So we use the state transition matrix dotted with P, dotted with the transpose, and we also introduce some noise Q. And Q is sampled from a normal distribution once more. And this is just to make things a bit more stable and account for all variables that could be introduced. So that's the first step. We first make an initial prediction, then we update a prediction once we get a new measurement. So let's say I measure the car's position Z. I measure it with my GPS sensor, and the value, and that's Z. So now our prediction from the previous slide was is it X spread, right? So X underscore pred gives us the new distance and the new velocity, but we really want to get the position because that's what we're interested in. So I multiply it with H, and actually it should be 10. My bad, it should be not 0, 1, 10. That gives us the first value of X, which is the position. Yeah, and then we calculate the error from the actual position and our prediction. This value is called the innovation. Keep that in mind. And then we calculate the Kalman gain as well. It's just that formula. So the way you can understand this intuitively is that it calculates the error of the prediction, and it shows how much does the prediction actually change with respect to the actual distance that we calculated. And R here is another noise matrix, which is sampled from a normal distribution. So now with all of these values, everything combined, we get a new prediction, which is X new, which is X spread plus K times the innovation from there. And if you look at the expanded version of this formula, it's just we're taking a weighting of the previous value of X, and we're multiplying it with a weight K. And we're taking 1 minus, okay, actually, we're multiplying the error Z with a weight K, and we're multiplying the previous prediction with 1 minus that weight K. So that's how much we want to account for the error that we calculated and the actual prediction. So that's how our final value gets weighted with 1 minus the weight times plus weight times the error. And a similar thing is done to calculate the new covariance matrix as well. And so now this is done in one dimension, and we want to calculate for 4 values, right? So it's just done for four more values. So the only difference is our transition matrix will now be 8 by 8, and so will our covariance matrix. So in this case, the covariance is just between two values, x is the speed and the velocity of the car in one direction. But now we want the covariance between every single variable that we have. So it'll be 8 by 8. And then everything else gets affected in the same way. The noise and everything, yeah. So now with the Kalman filter, we have new predictions, and at a new frame, we have new bounding boxes. So we want to match the new bounding boxes to our predictions as well. And how do we do this? With the assignment cost matrix. So for each pair of prediction and detection, we calculate a cost. And the cost is just IOU, again, intersection over union. So how much do they overlap divided by how much is the total area. And now we'll get a matrix of n by n detections to predictions. And essentially we want to find the smallest cost to match a prediction to a detection, right? Actually, can I lift this up? I want to write, or do I just write here? Fine then. I'll write here then. Yeah. Okay. So let's say after I get a new frame, I calculate my three predictions, like in the case that I have three objects, and I get my three new detections from my bounding box object detection algorithm. And the cost between each of these will be calculated using IOU. So I get like some cost, like 2.359. Now I have these 9 values. So I want to assign each detection to each prediction that I calculated. And a brute force would just be going through every single combination, which is n factorial, and that's super slow. So the algorithm used in the paper is the Hungarian algorithm. And essentially, this problem can be told as like a graph theory problem, where we have nodes T1, T2, T3, T1, T2, T3, and it can be thought of as a bipartite graph. And each edge between those two graphs are weighted by these values. And we want to find the lowest assignment of those edges to make a completely connected graph from this to this. And that's the assignment problem essentially. And the algorithm is it's just a bit big. I don't want to go over it too much. Yeah. And what this does is that at the end of the thing, we'll just find like the most optimal value for each detection. So it'll find like maybe that. So once you solve it, we'll find out that these values have, in our case, it's the highest cost because we want the highest IOU. And find these values will give us the matching of the detection. So this matches with that, this matches with that, and that will match with that prediction. And the runtime of our algorithm is O of n cubed, where n is the number of objects, and that's way better than O of n factorial from brute forcing. So now we have predictions, we have detections, and we associated them in our new frame. How do we manage these, I guess, tracks over the entire frame of the video? So whenever a new object enters the frame, we initialize all those values. The a-dimensional state space, we initialize the velocity as 0. And like I mentioned, we use large covariance values from the covariance matrix to reflect the uncertainty of our predictions. So we try to predict these tracks from multiple frames to make sure that this object is not just like a one-off object, it's there to stay. And after some time, if it's not being detected anymore, the object is just deleted after like T frames. Yeah, and this is a super simple algorithm in terms of the techniques used, but it fails when it comes to occlusions. So once we get occlusions in our frames, we don't detect those boxes anymore. So that's gone. And if we don't detect the boxes anymore, the Kalman filter will become more uncertain over time. And then after some time, the box is just deleted. And when the object comes back into the scene, it's thought of as a new object. So we don't want that error to happen. So the same authors made a new paper, Deep Sort, where they use a deep association metric. So you can see two new differences here. The initial thing is the same. They have a detection, and we get a bounding boxes. We put that into a Kalman filter, and then we have these two new association metrics, the Mahalanobis distance and a deep appearance descriptor. So previously, we just used IOU to associate the detections to their tracks, but now it's those two new things. So I mentioned from the Kalman filter topic that it doesn't just give out an estimate. The estimate belongs to a PDF, a probability, a distribution function. And when we get that a-dimensional state vector, trying to, I guess, see how similar it is to a different vector with just like a normal Euclidean distance, it's not a good metric to calculate the distance. So the authors use this metric, which is the Mahalanobis distance, and this incorporates the covariance matrix. And the covariance matrix is, it gives us information about how uncertain we are about our predictions. So we're trying to incorporate more information into our cost function. So that's that. In this case, D is our detection. So X, Y, width, height, or I mean, X, Y aspect ratio and height. And Y is our prediction, X, Y aspect ratio and height. And certain values are just discarded if they're not within like that interval of the chi-square distribution. It's just to make sure that we just keep like a small threshold. So with this function, we can associate motion and information across different tracks. But in my opinion, this is the real improvement. They use a deep appearance descriptor. So we also want to associate the appearance information of each detection. So how closely does each detection look like a previous detection? And they use a feature extractor for that. So this is just a regular CNN, which is used for classification. So we apply a bunch of filters from the previous slide, and the filters are made with different weights, and they apply these filters at different scales to learn different features at different scales. And at the end of this convolutional network, they get this one layer, which is like a long vector, and that's called the feature layer. This feature layer gets put into a fully connected layer to get the actual classification. So in the end, if you want to classify 10 objects, we'll want to connect this to a final layer of just 10 vectors, and then this fully connected layer will give the probability of how highly probable is that vector to belong to that class. Now, we just want a feature vector, so we don't care about the end part. We just want the flattened layer. And that layer describes all the features of an image. So now I get the feature layer for a bounding box, and I have the feature layer from the previous bounding box. How can I guess, figure out how closely similar those two features are? What's like a simple metric that I can use? Anyone? If you remember embeddings from like LLMs, how do they check how close the two embeddings are to each other? Even embeddings are just like a vector that represents a word. Exactly. It's just cosine similarity. So we have one vector that represents one image and another vector that represents a different image. And we can just use the cosine distance to see how closely they are to each other. And that's just the dot product of two vectors. So we keep a track of the appearance descriptors for each object for a bunch of frames, and frames in this case. And we see for each object for which descriptor does our new one match the closest with, and that will be our D2 distance. So now we have two distances, the distance from the motion and the distance from the appearance. And we just sum these values with a weighted scale, and that will be our new cost function. So so now we can get the new cost function, put that into our assignment problem, and then again assign each new track to each new detection. And that's how we track with deep sort. One issue, no, not an issue. Like the really good thing with this is that, oh, it handles occlusions extremely well. Why? So we keep track of appearances. So once an object goes behind an occlusion, we don't know what it looks like. But when it comes back, since we know from our previous tracks, we have a bunch of appearance descriptors, we'll match this with like a descriptor. We know it looks the same, and that's how we can like associate objects once more with occlusions. A downside in real practice is that it's a bit slow because now we have to train two networks, like a feature extractor and an object detection model. And I'm doing two forward passes each time. So not really. So sorry. Well, so like let's say, sorry, no. So we still want to extract features from objects of interest. So like if I only want to track cars, right? My thing needs to know what a car looks like. So yeah, but I figured yes. So in exactly. So in the case of the paper, that's what they do. Like the first few layers are taken from a pre-trained model, and then they train the last few layers for. No, they still need to train it at the end of the day. Like it needs to be done. So yeah, and this works really well in practice. It's just a bit slow. So there are many more approaches to a 2D object tracking where they don't like we improve on sort without doing re-identification with a deep association metric, with like more algorithms, and like everything that I've described so far has been like a two-stage process where we get the bounding box and then we try to track the bounding boxes across frames. Other models do a different thing where we input two different frames and the model itself will predict which objects move across multiple frames. And that's like a different whole subset of models, which I won't be talking about today. So now how do we move this into 3D? So if you think about 3D, it brings about a whole new range of issues and problems. So in a 2D object detection case, we just wanted to track XY coordinates across the camera's field of view. But in 3D, now we get a 3D box, so XYZ. Yeah, so we get like a 3D box, XYZ, along with height, width, length, and the three angles, yaw, pitch, and roll. So the object detection model in 3D must get all these three values. In practice, these models are just used for tracking cars and like objects moving on a stationary plane. So we can ignore the roll, but it's still, we need the pitch, like how is the car moving across the plane. So it's the same pipeline. We have 3D object detection, get the 3D bounding boxes, have our Kalman filter, get a prediction, associate those values, and then make new predictions. And then based on how long each track has been detected for, we either delete them or make new association, new tracks. So the most accurate method for 3D object detection is with LiDAR. And a LiDAR sensor is just, it's a device that emits a bunch of light waves in all directions. And then based on how long it takes for the light to reach back, we can create a point cloud. So a bunch of points in 3D space, which just shows the apparent location of objects in the frame. So you can think of it like placing a huge tarp across a 3D scene and then getting points from that tarp, and that'll be our point cloud. And just basic math to find out where a point is. So we have our point cloud, a bunch of points in 3D space. How do we get boxes from them? Yeah. So I won't be explaining like a specific architecture for 3D. I just go over like the current approaches used and the way they work. So we can treat the point cloud as these like representations. So point-based means you just take each point as it is. Voxel means you try to divide the point cloud into a bunch of subdivisions or cubes. And then we just treat those cubes as our inputs. A projection-based is you try to change the space of your point cloud. So instead of 3D, you try to project it onto like a 2D plane, like a surface. You can take a bird's eye view of the point cloud, so we can get like again a 2D surface. And then there's pillar-based where you take pillars of the 3D point cloud, like a 2D cuboidal embedding. And then graph-based, which is like you try to join points on the point cloud to make certain graphs across the entire space. So once we get these representations, we want to extract the features from them. And there's multiple feature extractors. They do them in a 3D space or in a 2D space. And like they work on both like point-based or voxel-based or all the other features. So a feature extractor in a detail is just from this. They want to learn features at different scales. So we have a CNN, a 3D based CNN or a 2D based CNN, and we apply filters of different scales, which will extract features of different scales. And then these features are then summed up, concatenated in multiple ways to extract new values. So now we have our features from our backbone, the first part of our network. How do we get the bounding boxes? With the main detector networks. So there are two types, anchor-based and anchor-free. Anchor-based are networks in which they assume that each bounding box will be of a fixed anchor shape. So they make a grid across the entire image of a bunch of tiny boxes. And they use these anchors to predict if a box on the actual scene aligns with an anchor that's in the network. And anchor-free networks are those which don't assume anything about the size of the boxes. They just try to predict the actual location XY. And then based on that, they leverage some more information, such as like the semantic information, like other objects in the scene, foreground objects, parts, and center points to figure out which orientation is the bounding box in, height, width, size, etc. And again, just like with 2D detection, there's two stages and there's two types, one stage and two stage. In two stage, we first get a proposals, and then we try to define those proposals into actual detections. In one stage, it all happens at the same time. I mean, like in one feed forward pass. Yeah, and that's how LiDAR detection works. So the issue with LiDAR is that it's really expensive to have a LiDAR sensor, like a good accurate sensor, because LiDAR can get very sparse over long distances. And it's also it becomes be very inaccurate in like weather conditions which are not so suitable for LiDAR, like in rain or fog. And sometimes there's also stuff like reflections of certain light waves, which can completely spoil the point cloud that we get. There was like a study that was done in which like a person, the authors, they used like a reflective metal with a LiDAR, and that metal just like it reflected all the light rays, which completely spoiled the point map. And if a tiny object like that can spoil the point map, and these point maps are what run our self-driving cars, it can just completely destroy the entire system. So it's a bit of a security like vulnerability, and I think that's why like Teslas don't have LiDARs right now. Like they all just work on stereo because it's cheaper. Um, so yeah. Okay. So we get our 3D bounding boxes. Now, the difference in 3D and 2D is that we need to make uh, the the Kalman filter predictions and associations. So for the Kalman filter, we have an extra value Z and an extra parameter, I mean, an extra value for the height of the length of the bounding box. So that's just increasing the dimension by an extra value in the Kalman filter. And that doesn't take much time to implement. It's just an extra value. And for the intersection over union or the cost matrix, instead of taking a 2D bird's eye view IOU, they take a 3D IOU where they find the enclosed volume of the two boxes. And that's used for the cost matrix. And there's like many types of IOU, like GIOU, SIOU, which improve on the basic IOU. And that's how they refine the predictions. And with that, you get 3D object tracking. Yeah, and that's it. Any questions? No? Okay.